When a star collapses and leaves behind a neutron star, it creates one of the strangest places in the universe. From the outside, it looks simple, a small sphere spinning in space only about the size of a city. But inside, the pressure is so extreme that matter is forced into forms we have never seen on Earth. The core of a neutron star is where our understanding of physics is tested to its limits. It is not enough to describe it with the rules we know from nuclear experiments or particle accelerators. Those tools can only mimic such conditions for the briefest instant. This mystery matters because it connects directly to some of the biggest questions in science. What happens when matter is crushed beyond the limits of atoms? Do exotic particles emerge, or do neutrons themselves break apart into quarks? Could the core of a neutron star be showing us a glimpse of the conditions that filled the universe in its earliest moments? We don't yet know, but each new discovery brings us closer to answering questions that go to the heart of physics and the nature of reality itself. When you look at a neutron star from the outside, it seems like a simple object, a tiny sphere spinning in space, sometimes flashing like a lighthouse if it's a pulsar. Neutron stars form from the explosive deaths of massive stars, typically those with 8 to 20 times the mass of our Sun. As the star exhausts its nuclear fuel, its core collapses under immense gravity during a supernova, compressing protons and electrons into neutrons until the pressure of densely packed neutrons halts the infall, leaving behind a compact remnant just 10 to 20 kilometers across. But the inside tells a completely different story. The deeper you go, the more alien it becomes. Scientists often describe the star's interior in layers, and each layer reveals a new side of matter under extreme pressure. At the very top lies the outer crust. You could think of this as the neutron star's skin, only a few hundred meters thick. Here, matter is arranged in a way we still recognize. Atomic nuclei packed together with electrons buzzing around, but even here, it's far from ordinary. The density is so high that what we would call solid on Earth is nothing compared to this. Imagine the hardest metals we know, like steel or tungsten. The crust of a neutron star is orders of magnitude stronger because every atom is crushed into its neighbor. It's believed to be the strongest material in the universe, and it explains why these stars can hold together under such crushing gravity. As you go deeper, you reach the inner crust, and this is where things begin to change in a fundamental way. The density rises past a critical point where neutrons are no longer bound inside atomic nuclei. They begin to drip out, flooding the spaces between them. This moment is called the neutron drip, and it transforms the crust from being a rigid lattice into something stranger, halfway between a solid and a superfluid bath. We cannot reproduce this environment in a laboratory, so we only infer its behavior from astrophysical observations and theory. For instance, some of the sudden jumps in a pulsar's rotation rate, known as glitches, are believed to be connected to how this layer interacts with the superfluid deeper inside. The Vela pulsar, which has shown repeated glitches, is one of the best pieces of evidence that something unusual is happening in this boundary region. Beneath the crust lies the outer core. This is the part that makes up most of the neutron star's mass. Here neutrons dominate, but they are not alone. Protons, electrons, and muons are mixed in as well. And under these extreme conditions, they start to act collectively. The neutrons may enter a superfluid state, flowing without any resistance. The protons are thought to form a superconductor, meaning they carry electrical currents with no energy loss. These states of matter are not exotic guesses. They are supported by both nuclear physics and astrophysical observations. For example, the way neutron stars cool over time matches the behavior expected if their cores are filled with superfluid neutrons, which change how heat is transported. The outer core is also where the magnetic personality of the neutron star may be shaped. Some stars are born with weak fields, while others become magnetars, with magnetic fields so powerful they can rip apart atoms from thousands of kilometers away. The difference may depend on how currents form and move in the superconducting layers of the outer core. This makes the outer core not just a region of dense particles, but also the engine for much of the behavior we detect from these stars. Finally, we come to the inner core, the region where our knowledge becomes most uncertain. The density here is several times greater than that of atomic nuclei. This is far beyond the reach of any experiment we can run on Earth. At these depths, it is possible that neutrons themselves can no longer remain intact. Theories suggest that heavier particles called hyperons could form, or that the neutrons might break down into quarks, their most basic components. If this happens, the inner core of a neutron star would be more like a dense soup of quarks and gluons, similar to the state of the universe just moments after the Big Bang. We don't know which of these scenarios is correct, but we do know that the properties of the inner core determine how massive a neutron star can be before collapsing into a black hole. This is why the discovery of stars like PSRJ 0740 plus 6620 is so important. It is among the heaviest neutron stars ever measured, with more than twice the mass of the Sun packed into a space only a few kilometers wide. Its existence tells us that the core must be stiff enough to resist collapse, ruling out some models that predicted softer, weaker equations of state. Each layer of a neutron star leaves its signature in the things we can observe. The crust influences how pulsars spin and glitch. The outer core explains the cooling rates and magnetic field strengths. The inner core defines the maximum mass the star can sustain. By linking these outward behaviors with what we think is happening inside, astronomers are building a picture of a place so extreme that it becomes one of the universe's most valuable laboratories for testing the laws of physics. When scientists talk about the deepest part of a neutron star, they often admit that this is where our knowledge fades into uncertainty. The inner core is a place where densities reach several times that of an atomic nucleus. To put that in perspective, nuclear matter is already so dense that a sugar cube of it would outweigh a mountain. Multiply that by a factor of 3 or more, and you are dealing with conditions that no experiment on Earth can fully recreate. In that environment, the familiar picture of matter made up of neutrons and protons may no longer hold true. One of the main possibilities is the appearance of hyperons. These are particles similar to protons and neutrons, but with one key difference: they contain at least one strange quark. Hyperons are predicted by the same physics that describes normal nuclear matter, and at high enough densities, it becomes energetically favorable for them to appear. Their presence, however, poses a problem. If hyperons form in large numbers, they tend to soften the equation of state, meaning the matter becomes easier to compress. That would make it difficult for a neutron star to support high masses. Yet we know from observations, such as PSRJ 0740 plus 6620, that some neutron stars can reach more than 2 solar masses. This conflict is known as the hyperon puzzle. It tells us that if hyperons do exist in neutron star cores, something else must also be at play to counteract their softening effect. Another possibility is the formation of meson condensates. Mesons are particles made of a quark and an antiquark, and under the right conditions, they could form a kind of collective state inside the core. Pion or kaon condensates have been proposed as candidates. If they exist, they would alter the pressure inside the star and could change how quickly the star cools. Cooling observations are already being used to look for hints of such exotic phases, but so far the evidence is still indirect. The most radical scenario involves the breakdown of neutrons and protons themselves. In this view, the inner core is not made of quark matter. Quarks are the fundamental constituents of protons and neutrons, and under extreme pressure, it's possible they become deconfined, free to move around in a dense soup. If this happens, the core of a neutron star would be similar to the state of matter that filled the universe only microseconds after the Big Bang. Some models even suggest the possibility of hybrid stars, where a neutron-rich outer core surrounds an inner quark matter core. Others go further and propose the existence of strange quark matter, made of up, down, and strange quarks, which could be more stable than ordinary nuclear matter. If true, then entire stars made of strange quark matter might exist in the universe, although none have been confirmed. The difficulty is that all these scenarios, hyperons, meson condensates, quark matter, leave subtle signatures that are hard to distinguish from one another with current observations. The differences show up in how compressible the star is, how it reacts during mergers, or how it cools over time. Gravitational wave detections, like those from GW170817, are starting to provide some of the necessary data, since the way two neutron stars distort each other before merging depends directly on the stiffness of their cores. But even with this progress, there's still no definitive answer as to which exotic states, if any, are actually present. This uncertainty isn't a weakness of science, it's part of what makes neutron stars so valuable. They force us to confront the limits of our theories. If we ever confirm quark matter in a neutron star, it would mean we found a stable remnant of the universe's earliest state. If hyperons are proven to exist, it would reshape how we understand strong interactions in dense matter. And if none of these exotic possibilities turn out to be true, that would also be a major discovery, because it would mean nuclear matter itself can withstand pressures far beyond what we ever expected. The challenge of studying the core of a neutron star is that we cannot drill into one or build a laboratory version on Earth. Everything we know has to come from the signals these stars send us across space. That means every measurement of mass, radius, cooling rate, or gravitational wave is like a clue. And over time, those clues build into a picture of what the core might contain. One of the most important tools we have today is NASA's NICER telescope, mounted on the International Space Station. NICER measures X-rays from pulsars with incredible precision, allowing scientists to estimate their size and mass. For example, observations of PSRJ 0030 plus 0451 gave us one of the first reliable radius measurements. By knowing both the mass and the radius of the star, researchers could narrow down the possible equations of state. If the core were too soft, the star would be smaller. If it were too stiff, the star would be larger. The actual results fell in between, ruling out some extreme models and showing that neutron star cores are neither extremely compressible nor impossibly rigid. Mass measurements also play a central role. The record-holding pulsar PSRJ 0740 plus 6620 weighs in at more than 2 solar masses. The existence of such a heavy neutron star tells us that the core must be able to withstand enormous pressure without collapsing into a black hole. Any model that predicts exotic matter but cannot support this much mass is immediately under suspicion. This is why the discovery of very massive neutron stars has been so influential. They force theorists to go back and refine their models of hyperons, quark matter, and other possibilities. Gravitational waves have opened a new way to study neutron star cores. When two neutron stars spiral into each other and merge, they produce ripples in space-time that can be detected here on Earth. The first event of this kind, GW170817, revealed how easily neutron stars deform under tidal forces during a merger. This property, called tidal deformability, is sensitive to how stiff the star's interior is. If the core is soft, the star squashes more easily, creating a stronger tidal signature. If the core is stiff, it resists, producing a different signal. By comparing the data with theoretical models, scientists are starting to pin down the range of possible core compositions. Even the irregular behavior of pulsars provides hints. Some pulsars suddenly speed up in what are called glitches. These glitches are thought to be caused by the transfer of angular momentum between the superfluid interior and the crust. By studying them in detail, researchers can learn about how superfluid neutrons move inside the star. The Vela pulsar is a classic example. Its frequent glitches have become a natural experiment in understanding the superfluid properties of the outer core. There are also signs from how neutron stars cool. Young neutron stars lose heat rapidly, and the exact cooling curve depends on the kinds of particles in the core. The neutron star in the Cassiopeia. A supernova remnant showed a surprisingly fast drop in temperature, which lined up with predictions of superfluidity in the core. That single object provided some of the strongest observational evidence yet that the interiors of neutron stars really do behave like superfluids. Together, these different lines of evidence, X-ray radius measurements, pulsar masses, gravitational waves, glitches, and cooling rates, are like puzzle pieces. Each one on its own cannot reveal the full picture, but combined they begin to outline what is happening deep inside. The picture that emerges is not final, but it is getting sharper. And with every new observation, we move closer to turning theory into confirmed knowledge about the densest matter in the universe. Even with the progress made in recent years, the core of a neutron star remains one of the most uncertain frontiers in physics. Every new observation helps to narrow the possibilities, but the questions that remain are fundamental. The first challenge is the equation of state, which is the relationship between pressure and density inside the star. For normal matter, we can describe this relationship with great accuracy. But for matter at densities several times higher than the atomic nucleus, the physics becomes far less certain. Different theoretical models predict very different outcomes. Some suggest the core should be relatively stiff, resisting compression strongly. Others predict a softer interior that is easier to compress. Both options fit certain sets of data, and the difficulty is finding enough constraints to decide which one reflects reality. The second challenge comes from the possibility of exotic matter. If hyperons, Meson condensates, or quark matter really do appear in the core, they should leave behind measurable effects. The problem is that these effects are subtle and can overlap with one another. For example, both hyperons and quark matter can soften the equation of state, making the star smaller and easier to compress. But so far, the differences between these scenarios are too small for our current instruments to separate clearly. This makes it hard to tell whether we are looking at evidence for one type of exotic matter or simply the limits of ordinary nuclear interactions. Another issue lies in connecting theory with observation. Laboratory experiments in nuclear physics, such as heavy ion collisions, give us valuable clues about how nuclear matter behaves at high densities. But they cannot reach the sustained pressures found in neutron star cores. The data we get from these experiments is useful, but it needs to be combined carefully with astronomical measurements. The challenge is that the two sets of information don't always match smoothly, leaving gaps in our understanding. Bridging those gaps requires both better theory and better data. Observational uncertainty is also a major problem. Measuring the mass and radius of a neutron star with precision is extremely difficult. Small errors can change the conclusions about the core dramatically. NICA, for example, has already improved our knowledge, but even its measurements leave room for multiple models to remain viable. Gravitational wave signals are also still limited. The event GW170817 provided valuable information, but it is only one merger. To really distinguish between competing models, scientists will need dozens of such events, each observed in detail. Cooling behavior adds another layer of complexity. While the rapid temperature drop in the Cassiopeia A neutron star seems to confirm superfluidity, the exact cooling rates depend on many uncertain factors. The presence of exotic particles, the size of pairing gaps in superfluid neutrons, and the details of neutrino emission processes all influence how a neutron star cools. Without more observations of young neutron stars, it is difficult to know whether Cassiopeia A represents a general case or a unique situation. There is also the fundamental question of limits. What is the maximum mass a neutron star can have before collapsing into a black hole? The discovery of neutron stars heavier than 2 solar masses has already reshaped the discussion. If we find even heavier ones, some models will be ruled out completely. On the other hand, if no heavier stars are ever found, it could mean nature enforces a strict boundary, possibly because exotic phases of matter make the core too soft to hold any more mass. All of these uncertainties show that we are still in the early stages of truly understanding neutron star cores. We are building a picture, but it is incomplete. Each measurement provides another constraint, yet many possibilities remain open. This is why neutron stars continue to attract so much attention. They represent a natural experiment, holding answers to questions that cannot be resolved in laboratories or particle accelerators. The challenge is learning how to interpret the limited signals they send us, and how to connect those signals to the hidden processes taking place deep inside. At first glance, studying the core of a neutron star might seem like a narrow field of astrophysics, interesting mainly to specialists. But the truth is that these objects sit at the crossroads of many different areas of science. They connect nuclear physics, particle physics, astrophysics, and even cosmology in ways that few other phenomena do. Understanding what happens inside them is not just about learning more about stars. It is about testing the very foundations of how matter and the universe work. One of the biggest reasons neutron stars matter is because they are the only place where we can study matter at densities far beyond the reach of Earth's laboratories. Particle accelerators, like the Large Hadron Collider, can smash nuclei together and briefly recreate conditions similar to those inside a neutron star. But these experiments last only fractions of a second and produce small volumes of matter. A neutron star, by contrast, maintains extreme density and pressure for millions of years. It is like having a permanent experiment set up by nature itself, and all we need to do is figure out how to read the results. Neutron stars also provide a bridge between nuclear physics and astrophysics. The same forces that govern the behavior of quarks and nucleons inside atomic nuclei are stretched to their limits in neutron star cores. If exotic states of matter, like quark matter or hyperons, exist, they would force us to revise our understanding of the strong nuclear force. This is the force that binds protons and neutrons together and, by extension, holds all atomic nuclei in existence. So a breakthrough in neutron star physics is also a breakthrough in our knowledge of the matter that makes up everything we see around us. Neutron stars also play a central role in gravitational wave astronomy. The merger of two neutron stars not only produces ripples in space-time, but also creates heavy elements like gold and platinum in the process. These mergers depend directly on how neutron stars are structured inside. The stiffness of the core affects how long they spiral around each other before merging, how much mass is ejected, and how bright the kilonova explosion becomes. By studying their cores, we are also learning about the origin of some of the most precious elements on Earth. There is a practical side to this knowledge as well. While it may not lead directly to new technology tomorrow, the history of science shows that fundamental discoveries often find unexpected applications. Superfluidity and superconductivity, both theorized and later confirmed in neutron stars, were first studied in terrestrial laboratories, and today they influence fields ranging from quantum computing to medical imaging. Understanding them in the most extreme environments in the universe could inspire new ways of applying them here. Perhaps most importantly, neutron star cores remind us that the universe is still full of unsolved mysteries. They show us that the matter we take for granted, protons, neutrons, electrons, is not as simple or as final as it seems. Under the right conditions, matter changes, reshapes itself, and reveals deeper layers of reality. In this infernal crucible of gravity and heat, ordinary nuclei yield to exotic states, perhaps seas of free quarks or hyperonic brews, echoing the universe's primordial moments. Neutron stars are nature's way of telling us that the story of matter is far from complete, a silent testimony that there is always more to discover, more to understand, and more to marvel at in the depths of the cosmos. When we talk about neutron stars, it's easy to focus on the numbers. Mass is heavier than the sun, squeezed into a sphere only a few kilometers wide, densities so extreme that a spoonful would outweigh a mountain. But the real fascination lies in what those numbers mean. They point us to an environment where matter behaves in ways we can barely predict. At the center of these stars is a place we cannot see directly, yet everything we do observe depends on it. The way pulsars spin, the way neutron stars merge, the way they cool, and the way they resist collapse into black holes all trace back to what is happening deep inside the core. Despite all of the progress made, the heart of a neutron star is still more mystery than certainty. We have clues that suggest neutrons form superfluids and protons create superconductors. We have evidence that the cores must be stiff enough to hold more than 2 solar masses without breaking down. And we have hints that exotic states of matter may be present, perhaps quarks or hyperons appearing in the deepest layers. But none of these ideas are confirmed beyond doubt. For every possibility we rule out, another set of questions appears, keeping the puzzle alive. This uncertainty is not a weakness of the science, but its driving force. It shows us that neutron stars are more than exotic objects. They are natural laboratories. They give us access to regimes of physics that no machine on Earth can reproduce. They connect the smallest particles with the largest cosmic events, tying the behavior of quarks to the mergers of stars and the creation of heavy elements. In their cores, the universe is showing us a glimpse of conditions that shaped the early cosmos and continue to influence it today. The mystery of what truly lies inside the core of a neutron star is unlikely to be solved with a single observation or a single theory. It will take a combination of precision measurements, new gravitational wave detections, better models, and creative thinking to piece the picture together. Each discovery moves us forward, narrowing the possibilities while reminding us how much is still unknown. For now, the core of a neutron star remains one of the last great secrets of astrophysics. It is a place where our current understanding of matter is tested to the breaking point. The fact that we can even ask what exists there is a sign of how far science has come. The fact that we cannot yet answer it is a reminder that the universe still holds mysteries that are bigger than us. That balance between knowledge and uncertainty is exactly what keeps neutron stars at the center of the conversation, and why their cores will continue to fascinate scientists and anyone curious about the deepest truths of the cosmos.